Howdy. The overall and objective of our robot was to simulate a dog who fetches or goes and retrieves an object and brings it back to its human. The main objective is for the robot to travel from point A to B, A being the starting position and B being where the bone is or the object it is retrieving. And then finally, once it acquires the bone, it would grab it and then bring it back to the starting position or relatively to where the starting position is. It's going to do that using global coordinates and SLAM, mainly from LiDAR, this the SLAM integration. And it's going to be able to avoid obstacles going there and back, whether that's dynamic or static obstacles. Once it gets to point B, its general location, which is an assumption we make, it will be able to identify the object using HSV filters, basically camera vision. And then once it has the object, it will grab it and then bring it back. So that's the basic objective of our robot Rex, as you can see. And thank you. I'll hand it off to my colleague.
So, core functionalities. So, for our original objective of Rex, our robot dog, we set a general outline on what we plan on implementing within our proposal and plan on developing a robot to simulate a dog. So, here are our core functionalities for Rex. So, it will provide obstacle avoidance capabilities through the use of a LiDAR sensor. Using computer vision through our W200 HP camera, it will utilize HSV filtering to locate a distinct object simulating a bone. Utilizing a 3D printed claw, we will utilize a SG90 servo motor. As seen below, here is our CAD file connecting to the servo motor to provide a grabbing and releasing mechanism. To the right, as you can see, is our distinct object in bright neon color simulating a bone. This allows for easy calibration for the HSV filtering through computer vision, as seen tested in Node-RED. So extended capabilities. So once our base outline defined by our proposal was implemented, we decided to expand on our project and implement extended capabilities. As mentioned, we wanted to simulate our robot be as similar as to a dog as possible. So in order to, increase the complexity of our project, we decided to implement and incorporate both audio input and audio output for our dog that allows us to prompt a dog to run a series of tasks when detected. So we were able to successfully implement general voice commands that would only activate after detecting its name, utilizing the HP W200 webcam's embedded microphone and an external Adafruit stereo speaker. So there were four main commands that were implemented. Bark, where an audio wave output would be outputted to simulate a barking sound. Spin, where the robot will rotate until the command stop is told. And fetch, where the object will locate its bone and stop only when prompted. So as mentioned, the command will only run when its name is called. For example, if I just said bark, it will remain in its idle state. If I instead said something like Rex, bark, through through audio transcribing, the robot will understand the command and provide an audio of it barking. Additionally, we utilize the LiDAR module to map out its surrounding environment. Overall, we expanded on our project by incorporating mapping as well as voice commands through the utilization of audio input and audio output, allowing us to create a project that more likely simulates a dog that can do cool tricks.
This is our final scuttle build/design. Here you can see where every component is located along with their corresponding labels. Each component is important and is vital to the operation of the project. The speaker is used for audio output when given a specific audio input. The H-bridge connects the motors to the Pi to allow for precise control. The LiDAR is used for SLAM and obstacle detection. The camera has an HSV mask over it to detect the object, as well as an embedded microphone used for audio input, and the grabber is used to retrieve the object and give it to the owner. The Pi connects everything together and is used for the operation of the whole system. This was our distribution of work at the end of the project. We believe that this was fair and left no one doing more work than anybody else. Dylan was in charge of testing the grabber along with the servo motor, as well as implementing the LiDAR and the HSV camera with the embedded microphone. He also programmed the voice commands through audio input and output scripts. Harsheet programmed the structure of the operating system as well as programmed the HSV filtering and calibration to detect the object. Caleb designed the grabber and the bone in Fusion 360 as well as fabricated and assembling them. Lucas programmed the audio-to-text speech processing as well as programming the path algorithm for obstacle avoidance. I designed the path for the obstacle avoidance as well as programmed the SLAM implementation.
During designing and testing the robot, we did face some issues and had to take some preventative measures in order to overcome these issues. For example, we faced issues with the I2C connections on the Pi. Specifically, the scuttle hat's multi-ports pins were bent out of place and had to be rebent, simply due to the fact that they were very fragile and prone to bending with the tiny amount of space that's provided on the scuttle hat when inserting the JST connectors. We also had some issues with the bounding box algorithm when working with the pathing script. The bounding box was the yellow box that was applied to a series of pixels that were detected when a color mask had been matched for the input frame. Due to the variable lighting in different environments, the image mask would sometimes false detect or not detect the object at all. The HSV value had to be fine-tuned in order to detect the cylinder properly. Also, implementing the full claw assembly with the SG90 servo onto the chassis was a bit of a challenge, specifically because the first time that we designed the claw, the design did not take into account that the aluminum extrusion would interfere with the servo mount. Hence, we had to delay servo testing by redesigning the claw, and this time, after the redesign and proper measurements, it did end up working. Finally, the voice command readings were also undetectable due to certain misinterpretations with the audio input. This basically happened due to background noise or the Scuttle and Vosk library not particularly picking up the words Rex or the bark and fetch commands. Hence, we utilized lists of similarly misinterpreted words and added those as a near accuracy for the Scuttle to pick up. So any other similar words that sounded similar to Rex or spin or fetch or bark would be counted as a valid command, and the Scuttle would interpret it and execute the appropriate task.
Howdy, this is Lucas. I will be covering the outcome of the final project for MXET 300. Our team achieved all the goals set out for us. We were able to detect and avoid objects using LiDAR. We were able to search and retrieve the bone using computer vision, and we were able to implement basic localization so that the robot can navigate to and from the search locations. We were able to register and respond to voice commands and to use external speakers as well, both of which were extra objectives that we decided on. So our team learned quite a bit as well. So the programming team worked a lot on speech-to-text processing using Vosk and integration of multiple modules. I worked quite a bit on the speech-to-text myself. And our electrical and mechanical teams learned quite a bit about 3D printing and troubleshooting electrical systems when things started going wrong on this. Thank you for listening to our presentation. Please have a great day.